So it's no mystery that depending on how you route your traces on your printed circuit board, especially differential pair traces, that it's going to affect your signal integrity. But how do you know or verify that your rules and best practices that you implement, we apply the rules and best practices, how do we know that it's actually going to work? And how can we know that if we change some things on a trace or a differential pair, especially at really high speed like PCIe, that we're going to get the same performance as if we routed it somewhere else on the PCB? That's what I'm going to do here in this video. I'll show you the impact on how when you're using the same PCB stack up, just how much change or difference there is when you route on one part of a PCB versus similar signals on another part of the PCB. We'll take a look at the variation. So let me show you what I'm going to do here. Here I have a board from Nvidia. This is an astounding piece of engineering and it's beautiful. It's a 10-layer printed circuit board that has a ton of traces, vias, micro vias, and an HDI stack up or high density interconnect stack up, and a lot of pins and connectors. And what this has, let me show you the different layers, are especially on layer 3, our PCIe. Okay. A lot of people are afraid of PCIe because you have to route them according to fiber weave and all that. So yeah, there are many things that can go wrong if you do not route your high speed signals very well. We're talking about like 20 gigabits per second and higher, although technically you are in the RF domain above 2.5 gigahertz or so, or above 1 gigahertz. But in 20 gigabits per second and 40 gigabits per second, you really have to pay attention to the field. In fact, you're routing microwave fields at this point, okay, at PCIe level Gen 4, Gen 5. So that's an overview of the board. What we're going to do is see how the changing of the layers via transitions and whatnot and the accompanying or nearby ground vias are going to affect the signal, the return path and all that, and how they show up and affect the signal integrity most importantly. I'll be demonstrating this in Allegro X with Sigrity X Aurora and the topology extractor. We're going to use simulation in a workflow to verify what our best practices are trying to do and to understand or see the fields and, well, see the signals and make sure that they are good. So let's get back into it. Here, what I like to do in my workflow is after I've set my constraints, routed everything, then I would go to Analyze Workflow Manager. And then in the Workflow Manager, look at the topology extraction workflow. This is to double check and verify signal integrity. Then I'll select my appropriate nets. The nets I'm most concerned about would be this UFI TX7P. So let's just select the net. And I'm going to, get rid of all that because this is going to be a tough simulation. Filter by name. Matter of fact, I don't even have to filter for them. I can just click on the nets and they'll show up. And then let's see about some differential pairs that are way in a different direction. Now, here's the thing. This board is very well routed. So you need to like intentionally introduce problems into the routing for this to be a problem. So let's go ahead and click here for these two differential pair nets. Okay, so I made sure to choose the differential pair that's on the upper right side of the PCB and then on the far left side of the PCB on layer 3. These are my PCIe. Let's go click apply, then OK. Next, let's view the 3D geometry to see what layers they transition through, get a feel for how these traces are actually routed. So looking at the traces and their routing topologies, we see DSP, SSRX. This is our receive differential pair here. And they go through three via transitions. Okay. Some large connector. Well, two via transitions actually from into a connector through the through pads. And then we have on our other differential pair routed here, coming up from, looks like the bottom layer, up through these layers, up to layer 3. Okay. So now with that shown, we're going to start our extraction. Now, if you've seen my other video, the extraction phase is where Sigrity X Aurora pulls up the topology extraction workbench. It models the dielectric material the dielectric layers, which have all the energy anyway, the electromagnetic fields, and the copper structure, does the equivalent impedances and all that, that would be very, very hard to calculate by hand, which is possible, just not feasible at all. At this point, and at certain high speeds, you have to simulate. So we're gonna test and see what a 1 gigahertz pulse going through these traces will look like. We'll compare them. We'll also test 5 gigahertz and then just keep going up in the gigahertz for Nyquist frequency for these high speed signals. So what I'm going to do now is go into the topology that's been extracted, and we're going to be comparing the signals that have been extracted here against different frequencies. First off, we have our differential pair that goes through here, and this is the receive part of the differential and our signals. We also have our connector, our chip U7, another connector, and another connector on the output here. Now, what is the subcircuit? It is your entire PCB stack up, modeling everything in your PCB design, the dielectric constant, the dissipation factor, or loss tangent, and everything in between, the copper, all of that. Now, what I like doing is testing different signal frequencies. Some of these will fail certain frequencies depending on how they're routed and what they are for. So that's exactly what we go to test. Not all routing paths are created equal. So what we're going to do is set up our analysis options and then see how they perform in comparison to each other. We'll start off with 1 gigahertz for signal injection, and then we will do the simulation. So we run that, and it's going to give us the eye diagrams for each of our signals. So C for signal D46, we have on the the D connector, D46 receive signal. This is what it looks like. I'm going to uncheck the rest of my signals and see just how this performs. Now, this is the combination of the positive, the plus and the minus, okay, on here for the differential. And when we look at the eye diagram, it looks great at 1 gigahertz. Let's look at the other signals. We have the eye diagram for the J6 connector. Doesn't seem to handle its differential signaling too well at 1 gigahertz. So that may need to be looked at if you want to push 1 gigahertz through there, but it's not intended to handle that. And then here we have J33, similar situation, it's to be expected. Now for our U7 chip, it's designed specifically to handle up to 1 gigahertz and likely beyond. So depending on your connector, chip, or what have you, you can route it in such a way that, hey, if it doesn't accept or handle differential signaling beyond 1 gigahertz, that's fine. We only need to handle up to 480 megabits per second or whatever the case is. And then you have your chips, which need to handle higher frequencies or higher gigabits per second, and those perform better. So we route them differently. So it really just depends on your application. Here, our chip does just fine at the 1 gigahertz range, and then for this eye diagram and performance. And if we look at the signal, it does its own thing for the RX, the received signal. Now, if we push this up, and the connectors, not so much. If we push this up, obviously our connectors are not going to do as well. We'll rerun the simulation. Now, rerunning the simulation at 2.5 gigahertz, the eye diagram is a bit more closed, and this is what it looks like here. If we're still within the acceptable range, then this is fine. If not, then you need to double check and reroute your signal traces for the gigabits per second speed that you're looking for. Okay, so this is how you would evaluate your different traces and routing paths for different signal speeds and signals in general. Okay, this is what I do to make sure that my design works right the first time. Go ahead, and if you do have Sigrity X Aurora and access to it, of course, then try it out and see what your performance is like. This is how you can tell whether your signals will perform or work on the PCB or not. And when I'm talking about routing decisions, I mean, even if you route the same length, maintain the same impedance and length matching and all that, you could choose just a different via, and that could dramatically or significantly change the performance because the via is additional trace material as well, right? So, and also how you route through your dielectrics and push electromagnetic field energy through the dielectrics, that's the ultimate decision maker when it comes to signal integrity, EMI, and everything else. So you have the same board, same layout, different routing decisions, different outcomes, different topologies, different results. Work simulation into your PCB and hardware design workflow so you can get your boards working right the first time.